in this video, let's implement a simple binary search tree data structure and include two instance methods. One is called add and one is called remove. And probably in future, we will also add in the traversal functions for the binary search tree data structure. So without further ado, let's get started. So first, binary search tree, just like a standard tree, needs a node to include inside the structure. All right, so needs a constructor, a data, and let's call it this dot data equals to data first, and this dot. Okay, in the standard one, we need a parent pointer, but in binary search tree, we are only pointing downwards. So left equals to left. Right equals to right. So you can see here, each node in a binary search tree is only going to have two children. Okay, left and right. And in here, let's implement the binary search tree. So, okay, so it's going to be called binary search tree, and it also needs a constructor, just like the standard tree. We can initialize it with root node, and equals to the what was called new node. Yes, and passing the data here, and we will say this dot property name root equals to our root node, and we are done. The basic attributes has been finished. Now we just need to add some functions. So let's add the first function, add function, and the add function should take single new value to be added, or new node, but based on your preference. So first thing we check is call function. Probably call it find place to add. You can call it whatever you want, but it's going to be a recursive function. So it needs two parameters. So the current value, okay, current node, and value to be inserted. We can stay using the new value here and initialize the recursion with with the first current node, that's going to be the root node and our new value. Alright, so let's write the function. So in here, the first thing we check, if check our new value is smaller than the current node dot data. If it's true, that means the node to be added is on the left hand side of the parent node. Okay. So in this case, let's check current node dot left is pointing to a position that's not being occupied. If that's the case, we can directly insert our new value by passing the new node and passing the new value in here, and be done with it. Perfect. But else, we need to move forward, meaning that we need to call this function again, passing the current node dot left, passing our new value again. Alright, we will do the same for the else if for our new value, for case when our new value is bigger than current node data. And if it's equals to current node dot data, meaning that this value has already been inserted, this way we do nothing. Alright. So okay. First we check again, this time it's right. Placeholder, if it's unoccupied, we passing, set it to the new node. Or else we recursively called the current node. Alright, this time a new value. Okay. So add function, I think, is complete. So let's add some value, test our solution, shall we? So standard tree. Okay, let's call it binary search tree, just to be a little bit explicit. Should be equals to new binary search tree. Okay. Data 5, just like the example. Let's call the add function. and we need to pass a 3, a 7, a 2, 4, 6, 8. 7, 2, 4, 6, 8. Then we can do a console.log our binary tree, search tree, and test our solution. So node binary search tree. Let's check. Root property is a node, has a value of 5, correct. Left anchor to a node has a value of 3, right anchor 7. Alright. Let's pass in the root node and access the left property. So it should populate 2 and 4 by right. Okay, 2 and 4, correct. Let's check the right. It should be 6 and 8. 6 and 8, correct. Let's move on. Our add function is correctly being implemented according to the rules. So what we can do here is write the remove function. So value to remove. It's going to be a lot of scenarios. Let's just break them point by point and deal with the smaller instance first. So let's call dot root, and it's going to be updated by a return value from a function that we later is going to implement. Also needs a current node, which is this dot root node, and value to remove. And so we can declare a function find place to remove, takes in a current node, takes in value to remove. Alright, so in here let's check first instance. So if value to remove is smaller than the current node dot data. So if this is the case, then we just need to check. So we should call current node dot left is equals to find place to remove, and pass in the current. You might wondering why we have to return a value. So the idea is we need to always return the current node inside our block that we are running, so that in instance like the current node is changed, updated, or having its anchors a little bit different than before, we will make sure that we have updated from bottom to up. Right. I hope it makes sense. It's if you don't know what I'm talking about, you can check out my video share that talk about the Heapsort. It's going to be this one, yeah. So meaning that our value to remove is on the right. Then we can say current node dot right find place to remove current node dot right, passing the value to remove. Always return the current node. Okay. So now if let's say value to remove is not bigger, not smaller, it means we have find our current node. Just to be explicit, let's use else if. And in here, there are a lot of scenarios. So what if we are trying to delete 8? So 8 doesn't have any children. So let's check it first. So if our current node dot left goes to null and is also equals to null. So in this case, what we can do is set the current node to null as well, and so that its parent node is it's using an anchor to point to the current node. It's going to point to now. So meaning that we have make that space cleaned up, and yeah, so therefore the current node is deleted. So what if it's not this case? Then it means maybe either one of them is now. So in that case, if one of the case is now, one of them is now. So okay, so in this case, if it's the left is now, then we could say current node equals to the current node dot right, and return the current node. So in this case, we want to one of them is empty. So when we want to delete 7, we just need to push what the reminding children upward by one space should be enough. So this is what I'm trying to implement right here. Okay, let's move on. Okay, so if none of these scenarios are met and none of the values are returned, it means we have reached an instance where both children exist. So that we need to, so let's say we want to delete 5, then we need to find the smallest element on the right hand side and push that to the front and replace the root node. So to do that, we need to have a function called find minimum node. We can declare it here because it can, what do you know, it might be used by other function as well. So find minimum node. It's a very simple function. So if the should be enough. But then we need to say something like constant dot minimum node and passing find. Okay, this dot find minimum node. This should be the tree, and we need to update this function later to bind keyword this. So what we can do here, find minimum node and passing the current node dot right. We want to find the smallest value on the right hand side, remember. Okay, so if we want to access the correct this keyword, we just need to call bind this. Yeah, this should be enough. Okay, and so current node should dot it. Let's not delete it this time. It's way more troublesome. We just update data. Okay, so n equals to minimum node dot data as well, and we should say that current node dot right is equals to okay, what's the find place to remove, passing the current node dot right, because we have used the minimum node, so we want to delete it. So we just so after this is done, we return the current node. Yeah, I think the remove function is finished. Let's test it out. So most complicated scenario would be to remove our root node 5 and 6 should be pushed forward. Let's test it out. So 6 root node property have a value of 6, right? And I have 3 and 7, and 7 the left anchor points to now, meaning that our original node, the stores value of 6 is being deleted. That's correct. One other scenario would be if we want to delete 7, so by right 8 will be pushed and 7 will be gone. So we will just say delete 7 and test it out. Okay, 8 is being pushed forward, left, and is now right. Is now, that's correct. Yeah. Basically this is how we can include a simple binary search tree data structure that has a add function and a remove function as well. I hope you like it. Thank you for watching.